All right. Good morning, everyone. So for today, we're gonna study about the quantization. This is a technique that you want to reduce the computational and memory cost when you try to inference. Okay, you just change the precision to be a lower one. And yeah, the good things that when you use this technique is like it gives a less memory, less energy when they try to consume, and yeah, it gives much more faster because in behind of the model it is a matrix multiplication, right? So if they have a low precision, it can give much more better, faster, not better that, but it's faster. But sometimes if you do this technique, it can lose some performance as well. So the family things that they have in these techniques, they have two ones. The first one is post-training quantization. The idea is just train first, okay, train or fine tune first, and then you just convert them with the low precision later. And another one is just the reverse thing, quantizational aware training. You just try to convert the weight first, okay, and then you try to fine tune or use pretend during that state. Yeah. The idea behind of the floating point is just this one. Let's say you have floating point. The the idea is that if you have a much number from the floating point, okay, it means that you can get the higher precision, but it trade off with the computational. Yeah, but the things that you want, yeah, let's say we have the floating point 32, we're gonna try to quantize to 8-bit instead, okay? So existing idea that they have two ones. The first one is called absolute quantization, and the second one is 0 point. The idea of the absolute max quantization is, let's say you have the original number, you just divided with the absolute maximum of the value inside the tensor, okay? And then you multiply with the scale that you want. So it's gonna mapping a range with that scale value. So it's come up with this equation. But if you wanna dequantize back, you just reword the equation, this one back, okay? So let's say I have this tensor, okay? So you can see that if I absolute and get a max value already, just keep 2 by 2 for me. And yeah, just do scale, check that how many scale value that I get. Okay, it give around 40. And yeah, let's say I want to quantify them. Yeah, I just put a scale, multiply with the original sensor. So now it give me this one. So you can see that it was mapping with the range that we set with the scaling factor. But if you want the quantile backs, okay, you just divide it with the scale back, okay. You put the quantile scale back. So now you keep the original value, but you can see that this is the one that what quantile, right? You can see that they have some errors position, value position inside as well. Like this one, original one is 0.1, but this one is come up with the 0.1008, okay? So I set the equation inside. Yeah, you can see that this one, even they get the quantile already, right? But the the things that inside behind of the detail of them is to be 4, okay? You can set them to be in 8 over here. Okay, if you want to make it a inch, not 4. Okay. The another idea is a 0 point. So the 0 point they consider about the asymmetric input distribution. Okay. So it's useful when you want to consider output about the value. So it's try to give a positive, not not try to keep in the positive value is gonna give a good useful. So the idea in this one, yeah, you just use scale again, but in this case they use 255 divided with the difference between maximum and the minimum of the tensor, and then you have to shift them. So you get the scale multiply with the mean again, okay, mean value again, and then you get rough and divided with the shifting point. So you're gonna get some 0 point value inside. And then yeah, you wanna control, you just do same as the absolute max, but you just add one more 0 point to shift the distribution. Okay. And if you wanna dequantile back, you just move from the positive to be negative 0 point instant and divide it with the scale. So I'll come up with the same tensor and I check minimum and the maximum length to set what is the value. So give me 6.2. Yeah, and do yeah, after I get an egg length, I put to the scale. So it give me around 41. Yeah, and then put to the 0 point equation. So it give me -5. So then now I can quantize already. So I just do scale with the tensor one and shifting with the 0 point. But so now you can see that this is the value that they have in the quartile from the 0 point. Okay. And if we compare this one with the C with the absolute max, yeah, it does not show the same one, but yeah, because this one has shift from this distribution already, but you can see that this value they also have -127 because they shift they add one more piece position values inside. Yeah, and let's say you do contact back, you also can. Yeah. And yeah, this is another one, but you can see that this one um it's also give an error as well. Even they do a shifting. Yeah. Yeah, and make sure that if you want to make them as int, you just have to set the touch in it as well. And then now we're gonna try to compare it with and evaluate the memory safe due to we do a quantization already. Okay, so I just call the model GPT-2, let's say, and tokenization, and you can see that if we use a model that get memory footprint, so this is the byte that they have. Okay, so let's say I ask for only one layer first. Okay, and then I put this weight, okay, inside the two functions that do about the absolute max and 0 point max. Okay, you can see that yeah, this is the original one, and it can be changed to the range that we set from the absolute and 0 point. But the things that you have to be careful in this one is about the PyTorch does not allow us, okay, to do int multiplication by default. So in the real scenario, you have to dequartile them to run the model, but store them as init instance. Okay. So another again, so yeah, I don't want only the first layer. Okay, so I try to get the entire of the weight. Okay. So we have the weight original, and then I just try to get each one from them and put to the function absolute to get the weight from the absolute one. And yeah, it's the same, put to the function quantize again and get the weight from the 0 point. And then yeah, I just want to make them as a pattern to be a one tensor. It should run again to get the values from this. Oh, I didn't run this one. Sorry. This and this. So I put them as concatenate. So maybe we can check a shape of them. How does it look like now? Yeah, we can see this is a one tensor, right? They just have only one shape inside. Okay, now I get the values of them already. Just see this example. Yeah, you can see this and this. Okay, so you can see that's is because they do about the quantile and then dequantile back. So it's most likely the same, but yeah, but we doesn't know that what is the things that they has changed. Okay, maybe the good thing that we can do is maybe we should plot them into the histogram tags. Okay, so this is the code that I checked, and yeah, you can see that we try to compare the original one with the absolute max and 0 point. We can see that the ways they have changed the value quite much from the previous one. They can be like a 0 or 0 blah blah blah, but you can see that both of the quantization is give a spike graph. Okay, so it means that the quantile has noisy the weight main one, so that's why most of the weight they give much more getting to the around not it's not a 0 value, but it's give a chain the value to be over here. Okay, and yeah, you see that we have model that has been quantized with the difference. Okay, so you can test them as well. So you just call model that generate, and then you put the input IDs that has mapped from the encoder already. No, from the encode tokenization already, and get the result. So you can see that even they get a lower one, but it can give the result. So yeah, and even you wanna let's say you wanna do the perplexity, yeah, you can check them as well. Yeah, but it's obviously that if you have an original one should be better than absolute or even 0 point. But yeah, it's trade off with the performance from the inference speed already. Yeah, that's why still useful. Like if you doesn't have like a good a bigger GPU, can use this technique to prevent that obstacle. And yeah, next I'll try to show this one at the last. This is a 8-bit quantization with the LM in 8. Okay. So you can see that previously that I said is the PyTorch does not give us to do the multiplication in 8. Okay. So in this paper they come up with the idea to fix that one. And another one that they do is about outlier problem. Okay. So even in this graph, I does not show the entry of the values, but they say that they have some values that it can be outlier. So this guy, they try to get that the outlier should be solved, should be not be the problem of the quantization. So they give the idea that they do about the vector wise, initially just absolute max. Okay. And then they introduce this thing, mixed precision quantization. This means that the outlier feature, okay, they are processed into the 14.16 and return to that precision, while the other values, okay, are changed to be in A format. As an outlier, they represent only 1.1% of the value. This effectively reduce the memory footprint of the model by twice. Okay. So we check with this one, the things that they come up. Okay. So first, so I'll change this one a bit. Would be wrong. Okay. So first, the things that you do, you have to extract column from the input hidden state X. Okay. Containing outlier feature using the custom threshold. And then the second one, yeah, you just perform a multiplication of the 14.16 instead. Okay. And outlier not linear in the vector wise quantization. Okay. And the last one, you just being quantize back from the 8. Yeah, from the 8 one that they have all the other values to 16 back and add them with outlier that they give a full 16. Yeah, you can see in this value image. Yeah, we just, let's say we have this one, you just do column y absolute quantile. So now you get the inch number 8, right? And then this is another one, you just do a low wise absolute again. And then you get inch number 8. So then now you just come up with another one. So you just do cross y with the cx and cw and divided with the absolute scale. This is the absolute max. Okay. And then you concatenate back from the original one that they said, and then yeah, you get the final output. But yeah, this this architecture is quite confused a bit, but if you want to use this technique, it's so easily. So for now, inside the Huggingface, let's say you want to call the model and you want to make them as an inference. For that technique, you just call load in 8 and set 2. Okay? You just set 2, so it's gonna quantize the model of your model already. So you can see that memory footprint that you have is quite small already. If you go back on the top in the model side original one, they have 500,000 around, but there's one that give only the 176 around thousand. Yeah. And yeah, we just try to plot again. You can see that yeah, in this case, because they give in age, right, they can give a different value that they count into the weight already. And if you want to do the text generation, you can also do. Yeah, you can see that this is original one, and this is the things that they want to quantize. And surprisingly that is like when I test this, yeah, the perplexity from the in it can keep much more better, but there is no conclusion yet, like why keep much better ones. Yeah, but you can also try to research with us. Okay.